This is bonus material for 1.4, the Tableau. This is practice in that proof theoretic validity. In case you didn't get the homework assignment very well, or in case you just want to see practice before you actually get started, this would be good. But you don't have to watch this in order to complete that. A quick review: here are the Tableau rules. You're going to see them again as we go along. Remember, what we're doing is we're in order to find validity, proof theoretic validity, we're taking the premises as our initial list and the negation of the conclusion. So we want to see, do these premises, can they live without the conclusion? If they can't, then we know that they entail the conclusion, that you have to have the conclusion if you have those premises. So we'll start with this, and we'll negate this whole thing. Right? And it looks like this. If P then Q, if R then Q, and then not this whole thing. Not if P or R then Q. Notice the not has to go outside of the whole parentheses, right? We put parentheses around this whole thing, and it goes outside of there. Alright, well, the first rule we'll apply is this one, the not if then. Notice I have to apply first to this this rule. I can't apply this rule, the inside parentheses, first, just like in Mathgana. You have to do these in order. So this is the inside parentheses. You have to go with the outermost first. You have to deal with those first. So I went to the negated if then statement. This part is like my A, right? This whole part right here is my A, and this part right here is my B. So the A and the not B, this is the A and this is the not B. So I check it off because I've already done it. I'm good. And also notice the reason that I chose to do this rule first is not because it's the conclusion, but because since it goes straight down, it doesn't branch out like this. I don't have to write a lot of extra stuff. So that's just a matter of making it simpler. Then I will split the P or R. So I have A or B goes to A, B, P or R, P, R. And remember, this is because at least one of these things is the case. So I split them off to say it might be this one and it might be this one. Maybe it's both, but I don't really need to account for that as long as at least one of them are accounted for. P or R, and then I'll start at the very top with the P then Q, which is like this, right? Not A and B, so it'll be not P and Q. Not P and Q, but you have to do them for each one, right? Every tip, so not P and Q. You got that settled? Notice also I have some things that are already closing out. P and not P. The branch, we said the branches close when you have something of the formula A and not A. I have P and not P. You can't have P and not P, that's a contradiction, so closed. You also have not Q and Q, closed. You also have not Q and Q, closed. So I only have to really worry about one, and I have this gentleman right here to deal with, if R then Q. So it's going to look like that, not R and Q, and I see R, not R, P, not P, closed. This is valid. All the branches are closed. That means that there's no way to make these two things work with the negation of this. Right? You can't make these two things work without having this guy right here. So you're saying for sure you have to have this guy if you have these two guys. And it just makes sense too if you think about it logically. What this is saying is if you have P then you have Q, and if you have R then you have Q. So if you have either one of these guys, you're going to get Q. Right? Either P or R, then you're going to get Q. And that's what this says. If P or R, then Q. Alright, the next one is if P, then both Q and R, and not R, then not P. We're going to see if this is valid. So we're saying if you have this statement that if you have P then you have Q and R, both Q and R, and you also know that you don't have R, then you know that you can't have P. So the way we start, we make an initial list with all the premises, if P then Q and R, and not R, and then we negate the conclusion to see if these guys can live without this. If they can, then this is invalid. If they cannot, then you know that every time you have these, you have to have this that's valid. So here's our initial list. P then Q and R, not negated this, not P, right? So the easiest one to do is just this one, not A then A. So not P, P. Sweet, got that done. Can't do anything to not R, right? That's a basic. It's an atomic formula right there. So I can't make it any smaller by these rules. So I'm left with this guy that you can see right here. The way it's going to break down, not P, and then Q and R. So not P, Q and R. Now you can see here I have P and not P, closed. Q and R look like this, Q, R, and I have not R here, not R, R there, closed. This is valid. Alright, the next one. Now notice this one doesn't have any premises. We're trying to see this whole thing, is it true, like just always? Is it always valid? So it says if you have P then Q, then you have Q, which sounds totally absurd, I know. But let's see if it works. So since we don't have any premises, our initial list won't have any premises, but we will have to have a negated conclusion. So we're going to put parentheses around this whole thing and say not that, right? Which is what we did here. And again, we have to work with the outermost first. So it's negating this material conditional, this little guy right here, this little horseshoe. When I look at the negated material conditional, it goes A, not B. So this should say this whole thing, not this thing. Oops, and that's what it says. P then Q, and not Q. So we got that done. This can't be reduced anymore, so I'll have to worry about this one. And I have this one in parentheses. This is not in parentheses, so this is the one I'm worried about. And it should split off, not A, B, right? So it should say not P then Q, and then Q. And there it is. So check that guy off. We did that one. And we're worried about this one rule, and it's this one right here. And it should just be P, not Q. There it is. I'm checking that off. Remember, I'm checking this off because if we want to say that we've proved that this is either closed or an open branches, this whole thing has to be completed, which means that you have to apply all the rules. So we're checking these off to make sure that we've applied all the rules that we can apply. Now I see not Q and Q here. Okay, that closes. But over here, I have not Q and not Q. I have P, but no, not P. This is an open branch. So this is invalid. I can't remember which way the slash goes. Is it that way or that way? But I'm pretty sure it's that way. Anyway, so let's see. We know that this is invalid. We know this is the only branch, so we can make a counter model based on this branch. We see that P is true and not Q is false because not Q is true. And the way we make counter models is we assign every propositional parameter 1 equals 1 that is not negated, and every one that is negated you assign a 0. So Q equals 0. Now this is actually wrong. So the way it should look is like this. P is 1, Q is 0. We want to see if we apply we assign these like this: 1s for P's and 0s for Q's. Then this whole thing should be 0. Right? This whole thing should be false. And remember our interpretation rule. So every time this equals 1 if A equals 0 or B equals 1, 0 otherwise. That's going to be important because those are the only ones we see. Here we have P equals 1 and Q equals 0, right? So that is, where are we? Right here. The first one does not equal 0. The second one does not equal 1. So this whole thing is a 0. Alright, so this whole thing is 0. And this whole thing is 0, right? And this one equals 1 if the first one equals 0 or the second one equals 1. Well, the first one equals 0, right here. So this one equals 1. Alright, so now this whole thing equals 1, and this whole thing equals 0. So this equals 1 if the first one equals 0 or the second one equals 1, which is not true, right? This one equals 1 and this one equals 0. So otherwise it is 0. There it is. Your counter model is P equals 1 and Q equals 0, and it shows that right here, that this whole thing is false. Alright, last one. We have if P then Q, and if not P then Q, then not Q. Alright, that's a substantial sentence, but notice before we move on, notice there are no premises, so we're going to negate this whole thing, right? So I will say not this whole thing. We're looking at the outermost parentheses, that's the one that we're worried about, and so this is the outermost, this applies to the outermost one. It's all of these guys right here are A, and this one right here is B. So we're saying not that, right? Not if A then B, which looks like this. And it'll go down to A and not B. So this whole thing should go next, and then not Q should be next, like that. Right? So I'll check this one off. This is easy to get rid of, right? We have it right here. Perfect. This is actually also easy to get rid of, the and. They go straight down just like that. So it should look like, oops, I'm sorry, I forgot to do that. So this one should look like that. If P then Q here, if not P then Q here, check. Alright. Now both of these guys look just like these guys. So it'll be, first one goes to not, second one goes to yes. So the first one, if P then Q, not P or Q, and you can see then the last one we're going to have not P then Q. It's going to do the same thing, but it's going to be not P, right? And Q, and you have to do it on both sides. And then these nots are easy to get rid of, right? P. So I have P and not P closed out. Q, not P, Q. I don't have any not Q's. I don't have any P's. This is an open branch. I have P here, Q, Q. I don't have any not Q's or not P's. This is an open branch. And I have a string full of Q's here. This is an open branch. So now I could have 3 counter models because I have 3 different open branches if I wanted to. We're only going to go with the leftmost one just for fun. So we assign P a 0, right, because it has a not sign next to it, and that's our rule. We say this one is a 0, P is a 0, and we say Q is a 1 because it's not negated. So here's our counter model. P equals 0, Q equals 1. Alright, so let's divvy these out. All the P's get 0s, all the Q's get 1s. Like that. Okay, we'll go with the inside parentheses first. 0, 1. What is this one? Well, it's an if-then statement. So it equals 1 if the first one is 0 or the second one is 1. Both of those are true, so this is a 1. This, I have to worry about the not first before I can move on to the whole if-then. So not A equals 1 if A equals 0. So this is a 1. So now I have a 1 and a 1 here. This equals 1 if either one of them is 1. I mean, if the second one is 1, and it is. So this whole thing is 1. So now I have 1, 1. Again, this is 1 if the second one is 1, which it is. So this whole thing is 1. So now this whole front part right here is 1, is true. And now I have the not Q. So if it's Q here, and the not tells me if A equals 0, then this will equal 1, but otherwise it's 0. So this is a 0. So this whole thing right here is 0. So I have a 1 and a 0. First one is 1, the second one is 0. If you look at this right here, the if-then again, if the first one is 0 or the second one is 1, then this whole thing is 1. Otherwise it's 0. This one is going to be 0. Alright, so we've just shown if P is false and Q is true, then this thing will be false. So this is an invalid inference. And that's all for the examples.